Look at our solar system, and you'll spot a clear division of labor. Small planets are hard, rocky spheres like Earth or Mars. Massive planets are puffy, swirling balls of gas like Jupiter or Neptune. For decades, we assumed the rest of the universe followed this exact blueprint. To test that assumption against the thousands of worlds we've discovered beyond our own neighborhood, astronomers plot them on a scatter chart. They measure a planet's physical width, its radius, along the bottom, and its density, how tightly packed its matter is, up the side. When you chart out the data, distinct families start to emerge. Down here in the lower left, we find the super-Earths. These are planets with a relatively modest radius, but a high density, meaning they're solid rock and iron. Move a bit further right, and another massive group forms. These are the sub-Neptunes. They are physically wider than super-Earths, but their density drops significantly. They take up a lot of space, but they're filled with lightweight, puffy atmospheres. For years, this clean separation of data points served as the gold standard rulebook for planetary physics. A planet's width strictly dictated its composition. The math told us exactly what kind of worlds the universe was allowed to build. Then, telescopes locked onto a distant object orbiting a small star. Astronomers named it GJ523b, also known as Weak-Horse Planet, and it broke the math. Look what happens when we drop the measurements for Weak-Horse Planet onto our map. It misses both of our comfortable categories. It sits completely isolated, hovering above and right of the super-Earths, and totally disconnected from the sub-Neptunes below it. Based on the strict laws of planetary formation mapped out in front of us, a dot in this exact coordinate space is a contradiction. A planet with these proportions physically shouldn't exist. To understand the problem, we have to look at the raw numbers. Let's start with its width. GJ523b has a radius 2.5 times that of Earth. Under normal circumstances, a radius of 2.5 guarantees a certain type of world. It's wide enough that its gravity should have collected a massive, thick envelope of hydrogen and helium gas, making it a classic sub-Neptune. But calculating its pole on its host star revealed its true mass. GJ523b weighs an astonishing 23 times as much as Earth. Take those 23 Earths and crush them down into a sphere just 2.5 times wider than our planet. That kind of intense compression destroys the gas giant theory. You cannot pack 23 Earth masses into a space that tight if it's filled with lightweight gas. The object has to be composed almost entirely of solid, hypercompacted rock. When you run the final math, dividing that massive weight by that tight volume, you get a density hovering right around 7.5 grams per cubic centimeter. Look at the contrast. Gas-rich worlds on the 2.5 radius line plummet to a density between 2 and 4. A density of 7.5 separates Weak-Horse Planet as a distinct species. Astronomers claimed this high-density zone for a new classification, the mega-Earths. This new class proves that a solid, rocky core can scale up to gigantic proportions we previously thought were strictly reserved for gas giants. The measurements for GJ523b highlight a severe blind spot in early astronomy. It forces us to admit that our own solar system is a deeply inadequate sample size. The neat divide between small rocks and large gas clouds that we see locally simply doesn't hold up out in deep space. The mechanisms that forge worlds in the vacuum of space are vastly more capable of producing intense physical extremes than our early models predicted. Our map of the universe is still being drafted in real time. And every time we try to box the cosmos into a neat, predictable set of rules, the universe provides an anomaly like GJ523b to crush those boxes.